Good afternoon. I'm Alma Robert J. Blassett, Dean of Engineering. And welcome and thank you for coming. Unfortunately, I do not believe Professor Ulaby is here to join us, but I'm really happy to see you here, Flynn, because I can't do this without you. So collegiate professorships are among the highest honor the college bestows upon members of the faculty. They acknowledge a faculty member's contributions to research, teaching, and service. They help us attract, reward, and retain outstanding faculty talent. Typically, these professorships are funded by the College of Engineering, and often they're named after former faculty members who made substantial scholarly contributions while at Michigan. The collegiate professorship is named for Fawwaz T. Ulaby, Arthur F. Thurnow Professor Emeritus, Emmett Leith, Distinguished University Professor Emeritus of Electrical Engineering and Computer Science, and Professor Emeritus of Electrical Engineering and Computer Science. Fawwaz is a global leader in the fields of terahertz technology and microwave remote sensing. Over the past 5 decades, and nearly 4 of them at the University of Michigan, Fawwaz was a model for what we mean when we say leaders invest. He has an inspiring list of accomplishments, including membership in the National Academy of Engineering, receiving the IEEE Edison Medal, whose list of recipients in the past include Alexander Graham Bell and Nikola Tesla, designing the first radar to fly in space, publishing more than 700 scientific papers and 16 books, and creating the free electrical engineering textbook initiative, which has saved students an estimated $10 million in textbook costs, if not more. And directing numerous interdisciplinary NASA-funded projects aimed at developing high-resolution satellite radar sensors for mapping Earth's terrestrial environment. He was also an inspiring and revered teacher. His students have described him as one of the best professors and people they've ever known. He truly made this field and the university far stronger than how he found it. It is fitting that the collegiate professorship bearing his name is being presented today to another premier scholar, educator, and researcher in the field. Congratulations to the Fawwaz T. Ulaby Collegiate Professor of Electrical and Computer Engineering, Dr. Michael Flynn. We'll now hear from Dr. Ming'an Liu, Peter and Evelyn Fu's Chair of Electrical and Computer Engineering.
Thank you, Alec.
For the recording, I think because there are people hybrid.
Good afternoon, everyone. My name is Ming'an Liu. I'm the Chair of Electrical and Computer Engineering. I'd also like to extend a welcome to everybody here, faculty, colleagues, staff, students. It warms the heart to see how happy they are for you. And also welcome Mike's family, his wife Linda, and his son Corey. And also a special welcome to Mike's former PhD advisor, Professor David Ostock, who traveled here on this occasion. It gives me great pleasure whenever I am standing here as the chair, giving such honor to our faculty. Wish I could say I had a hand in this, but alas, no. I will shortly invite Professor Jin Yajang to come up here and talk about Mike's many contributions in research. I just want to say a few words about how Mike has been a tremendous colleague and mentor to our students. I had first-hand experience with that for a few years. Mike was our associate chair for graduate affairs. He really dedicated himself to the job. He was the one who essentially wrote out the new qualifying exam system we have in ECE after we merged the 2 graduate degree programs. So that was tremendous effort. I also know Mike is absolutely dedicated to his students, not just his own students, but graduate students, undergrad students at large within ECE, and many of our students are truly grateful for his mentoring. And for that, Mike received the College of Engineering Excellence in Education Award, as well as the Rackham Distinguished Mentor Award. So with that, I will say thank you, Professor Michael Flynn, for being such I'm grateful that you are a part of the ECE family. And I'll hand this over to Jinya.
Hi, everyone. It's my honor and privilege to be here today to speak for my colleague and good friend, Mike Flynn. Mike and I have been on at least a dozen projects together over the last 10 plus years. And if I have to sum up these projects I did with Mike, they have always been the really hard ones that received very little glory. And then after the end of each one, we swore we would never do it again. And then a year later, somehow, Mike was able to get me back to the same spot again. So Mike is like this, the type of person who truly enjoys solving very hard problems, and yet he always tends to shy away from the limelight. So Mike is one of the world's top scholars in the area of analog and mixed-signal integrated circuits and systems. And I do not need to enumerate all his breakthrough contributions and also technical achievements here. So despite his status in the field, for those of you who actually know Mike, he's extremely approachable and humble. So quoting one of his students, Mike never overjudges your idea. Even if someone comes up with something that may sound crazy, Mike will only point out the difficulty and encourage you to figure out whether it is really feasible or not. And Mike's nurturing style provides his students and his collaborators, like myself, plenty of room to find our comfortable space, and also to innovate and grow together. And yet, at every critical juncture, you'll see that Mike was always able to inspire and provide crucial inputs to make very successful projects. So I find working with Mike a rewarding journey, and despite how difficult these projects are. So over the course of working with Mike, I actually got to know many of his students, including many of his former students. And one recurring theme I keep hearing from the students is Mike's influence on them at a personal level. Especially Mike's care of each personal circumstance, difficulty, and constraint, and his effort to always try to work out the best possible path and plan for each student. And many of his former students told me that Mike has been their lifelong mentor and role model. And his mentoring not only conveys knowledge and original ideas, but also stresses the values of integrity and pride in one's work. And for the same reason, I also consider Mike my own lifelong role model. But I must admit that I'll probably never be able to match how nice he treats his students. So sorry. So in the end, I'd like to end my remark by saying that it's truly fitting for Mike's professorship to be named after Professor Fawwaz Ulaby. Like Fawwaz, Mike is a highly accomplished leader of his field and a decorated educator and mentor who have made many noted impacts on his students and colleagues. So let's congratulate Mike on this very well-deserved recognition, and we're all very happy for you, Mike. Thank you.
Thank you, Zenia and Alec. It's really too much limelight for me to make. Anyway, I really appreciate this honor.
Yeah, got it. Yeah, assistance from the dean there. Very much appreciated. Yeah. Okay. So thanks so much for all of you for coming here. I really appreciate it, and I really appreciate this honor. Thanks so much to Zenga. And I know those problems were really hard. And Zenga has been a great friend over the years, and we've done so much together. So I want to talk about my research, and a lot of it is about analog to digital interfaces, analog to digital conversion. And the title of the talk is From Analog to Digital and Back Again. And we'll see how the back again fits in later towards the end of the talk. But first, I want to quickly thank the people who have been so helpful to me over the years. There's my family, of course, and Linda and Corey there are in the front. And I have two boys who are busy today. Thankfully, my parents are still with us. My dad is going to be 93 this year. I grew up on a dairy farm in Ireland, and my dad finished school when he was 14. My mom got a high school education, but their kids were the first generation to go to college. And all four of us ended up with graduate degrees, and two of us are professors in the US. And really, it's due to the sacrifices and the dedication to education from my parents. You know, the key thing to our success as academics is really our students, and we really kind of bask in the glory of our students. And I've had so many fantastic students over the years, and lots of them are here today, including two former students. My first PhD student at Michigan, Fawwaz T, is here today. You know, it's been great working with students. And what I found is that every student brings their own unique skills and contributions, and that's really true. I'm also super delighted that my PhD advisor, Dave Alstott, is here. And I think what many of us know is the relationship with your advisor goes on for your whole career. And I'm really happy, you know, to have been lucky to have Dave as an advisor. There's, you know, what I view, looking back on my life, so much of life is due to luck. And just meeting Dave was such a you know, very lucky thing for me. Also, I want to thank the colleagues in the department and ECE. We have you know, wonderful staff and faculty. You know, Zenga has been great over the years. I have wonderful colleagues in MICL. Those are the circuits faculty. And you know, I want to particularly thank four colleagues who were very important at the start of my career at Michigan, particularly Ken Wise, Rich Brown, George Haddad, and Khalil Najafi. And you know, starting off as a professor is so hard, and the help and encouragement from those faculty was really vital to me. Also, I want to thank Fawwaz. Fawwaz has been a true inspiration, and I look at Fawwaz, and Fawwaz is an outstanding researcher, you know, outstanding contributions to service. And something I only appreciated over the last few years is how dedicated he is to students and teaching. And I learned that he meets individually with all the students in all his classes. And that's something I try to do now, and it's so difficult. But, you know, Fawwaz, I don't know, he seems to do everything and excel in everything and still be a very good person as well. So, analog and digital. I mean, a good way of explaining analog and digital is watches, right? So there's a very expensive Shinola watch on the left there, and on the right is the classic Casio digital watch. This is actually from MoMA. It's considered, you know, a design masterpiece. It's a 50-year-old design now. So, you know, the key distinction here is that analog is continuously variable. Like the position of the hand, there's an infinite number of positions there. And a definition of analog then is relating, this is from the Merriam-Webster dictionary, a continuously variable physical quantity. Whereas digital is, you know, discrete, right? So now it's interesting to put into Google, analog is better. That's something I'd like to see. And that gets 280 million results. So that sounds like a good result. And then I thought, okay, I better qualify that by trying digital is better. 3.28 billion results. So yeah, I don't know. I still think analog is better. But really, for me, the research, it's at the interface between analog and digital. And on the plot here, it shows all these different real-world applications, you know, wireless communication, sensors, you know, microphones, even communicating to the brain, which I'll talk about later a bit as well. Those are things that we need to work with in the real world, but when we process those signals, we do that in the digital domain. So a lot of the research in my group has been on the interface going in and out between the analog domain and the digital domain. And one of the tougher problems in that regard is actually the analog to digital conversion. So let's talk about that. And I want to talk about it in a way that's accessible to everybody. And I've spent about a month making these slides and trying to figure out how can I present these concepts that, you know, that will be, you know, accessible to people and will make sense. Well, this is about as complicated as I'm going to show. On the left there's a kind of a classic signal flow where you have some sort of analog signal, like a sensor or a wireless signal. The first thing you do is you amplify that signal, and then you filter it, and then you put it into an ADC, that's an analog to digital converter, and then you do digital processing. So a lot of our work over, in my career here has been on analog to digital conversion. And that was considered to be a bottleneck about 20 years ago, but something remarkable happened. And what happened is, if you look across time over a 20-year period, the vertical axis there is the figure of merit to do with energy efficiency. That's improved by 3 orders of magnitude, right? Now, that's not just about Moore's law and scaling. So much of this is about technique. So these are from my own students, and if you look from other groups, you'll see similar trends, right? So it's pretty remarkable. Now, I want to talk about one type of analog to digital conversion technique, and it's called successive approximation. And it turns out to be, in some ways, the oldest technique. This is from the Book of the Dead. Depictions like this are about 3,500 years old, right? So this is a balanced scale. And when you're weighing something, you're essentially doing an analog to digital conversion. I actually love this pictogram here. In the middle is Anubis, and Osiris is on the right. And what's happening here is in the afterlife, somebody's heart is being weighed and compared to the weight of one of Maat's feathers, right? So depending on if your heart was heavier or lighter than a feather, depends on where you go in the afterlife. And on top there's a baboon, and the baboon is the god Thoth who keeps track of stuff in the afterlife. Now, when we do weighing, like there's a bird there being weighed, we're actually doing a binary kind of operation. And I'm showing here binary weights. You could have other kinds of weights too, but it wouldn't be as efficient. And you might start off by putting on, say, 4 kgs. That's too much. Then you go down to 2 kgs, and then you'd continue on in that way. And each time you'd half the amount of weight that you'd add on or subtract on. And what you're getting in that process is that you're getting 1 bit of information per cycle. And that's how successive approximation ADCs work. They get 1 bit of information per cycle. And if we're doing this in an electrical system, we don't have a balance, but instead we have something that samples the signal, and then this triangle signal is a symbol as a comparator, and the DAC represents the weight that you put on the other side of the balance. And the finite state machine is the thing that's guiding this. It's like Thoth in the afterlife or the human that's doing the weighing. And just to give a quick example of that, if we have, say, a scale going from 0 to 1, and we put in a signal of 0.7, well, the first decision would be to see, are we in the top half or in the bottom half? Are we bigger or smaller than 0.5? So you'd put 0.5 on the other side of the scale there. And then you see, okay, well, it's bigger than 0.5. And then on to the next cycle, are we bigger or less than 0.75, and so on. So we're getting 1 bit of information as we go along. Now, this happens to be an exquisitely efficient way of doing analog to digital conversion, especially in modern technologies. Now, one sort of drawback with this is, of course, that it's going to be limited in terms of conversion speed. So now let's see how you'd actually do this on a chip. Well, on a chip, you're not going to have weights. So the closest thing you can have to, maybe as an analogy for weights, would be capacitors. So in this case, this is a 3-bit ADC, and we can see the weights going up. We have C, 2C, and 4C. And if you wanted more resolution, you'd have 8C, 16C, and so on. So this is a 3-bit ADC. Now, the problem with this architecture was actually invented in Berkeley in the early 1970s. It's super famous. It gets used in every device. There's one of these. The problem with it, as you increase the resolution, you need to do more and more steps. And a lot of research in mixed signal systems and AD converters is how do we do better. So I want to show you a few very clever ideas that my students had, which had a tremendous impact on the industry and on research. So this is the first one here. So if we take, and I'm depicting this with the Anubis balance here, we're going to have a SAR ADC. We put in the input, and from the ADC, we're going to get a digital code coming out. But we're also going to capture something called the residue. That's going to be the little bit of weight that we didn't count with the number, right? And we're going to take that residue, we're going to gain it up, and we're going to get another SAR ADC, and we're going to process that residue. Now, the two different SAR ADCs, those can work in a pipeline. So you're going to drastically increase the throughput, right? But you're going to keep the energy efficiency. And this architecture that was invented by my student Chan-Chi Lee more than 10 years ago, this is called the SAR-assisted pipeline, and it's used in so many places. Now, there's another way we can improve this, and there's another clever architecture which is a bit more recent, but recently it's having a huge impact. So let me show you this. This is a different kind of idea. We're going to, again, have a SAR ADC, and the SAR ADC is going to produce a digital number, and it also produces a residue. But what we're going to do with the residue is we're going to pass it forward in time to the next conversion. So we say, well, I didn't consider this yesterday, so let me add it in for today, and I'm going to add it into the new conversion and take care of it today. And this architecture is a noise-shaping SAR ADC. And this is something now that's used in so many converters out there. So it seems like a relatively simple idea, but it works super well. So those are two examples of techniques that my students came up with which improved analog to digital conversion. What I want to talk about now is I want to talk about some applications. So at the core of our research, we build analog to digital converters of different types and things for clock timing called PLLs. And then over the years, we've moved outwards to the applications because the applications are so interesting nowadays. And we can build interfaces that are more tailored to the application. So we do things like brain-machine interfaces, we do analog computing, and we do radar imaging and so on. So I want to talk first about some of the work we've done on brain-machine interfaces. And Parag is here, so I started off working on this with Parag several years ago. And it's been fun collaborating with people in the med school. It's one of the great things about Michigan. And this is a collaboration that I'm going to talk about over the next few slides. It's with Yusik Yoon and Parag. And one of the big challenges in treating brain disorders is, monitoring the onset of the disorders and then trying to figure out if you're treating the disorder properly. So what you'd like to do, say for a disease like epilepsy, would be to measure the brain state, and then if something is coming on, you want to stimulate, right? So that's sort of the holy grail for these implanted devices. Now, one big challenge is that when you're stimulating to treat a disease, it can be very hard to tell if you're properly suppressing the disease because it's like shouting to someone and they're whispering to you. It's very hard to hear what they're saying. So the artifacts that you get from stimulation, those can just look like the symptoms of the disease. And this is kind of interesting here. This shows a neuron here. We've got a stimulation going on here. We're trying to measure a very tiny signal coming back from the neurons. But that stimulation that we're applying, it's being picked up by the recording, and it's just drowning out everything. So in collaboration with Yusik, Yusik and I co-advised a student. We came up with an adaptive system that would actually learn over time the response to the stimulation and subtract that out from what we were recording. So when we were recording, we'd get a clean signal. And we built a chip to do that. And here's an example of this system working with an animal brain. So it's a little bit complicated to see, but we'll figure it out. So the horizontal axis here is time, and we're continuously stimulating here. When we turn on the chip first, we're recording, and all the recording is seeing when we're turning on is the noise from the stimulation. We're not seeing the real signal coming back. But over time, the chip understands the response to the stimulation and adaptively suppresses the stimulation artifacts. So after a while, we just see the signal that we're interested in. So that's a very interesting application because it combines signal processing analog to digital interfaces, and this domain knowledge in brain systems. Now, here's another very different sort of application area that we've been working on heavily. And this is for wireless beamforming. You know, like the capacity of your phones keeps getting higher and higher. And one way that the phones and the wireless system work better and better is that instead of using one antenna, they use multiple antennas, and they can steer the wireless signal to your handset, or you can point to, you know, another device or whatever. And this was actually invented more than 100 years ago. So this is from a Nobel Prize speech from 1909, and this is, you know, one of the pictures from that speech. And actually, you can read this speech, and it's really nicely written. It's surprisingly well written. Now, this technique has been, you know, built up tremendously over the years, and this is one of my favorite photos of this. It's a little bit scary. This is the missile defense system. This was one of the stations in Alaska. It's called paved. This thing is a couple hundred feet high. There's thousands of antennas there, and this is for tracking potential missiles that would come in, right? Hopefully they never see anything, but you know, it's important to do it. Now, we've been doing this sort of system, but we've been doing it on chip level. And this chip here was built by my students a few years ago. It's the first single chip digital millimeter wave beamformer, right? So you can see there's a single chip. It's about this size. The top there shows the antenna array, and on the bottom, it's this chip that's connected. The chip is just 3 millimeters on the side. So I'm going to give you a little bit of context here, but there won't be too much hard stuff. So you have an array of antennas, and what you can do is you can process the signals coming from those antennas to point in a particular direction. So let's see how to do that. Well, this shows the array of antennas here. There's 4 of them in this case. And let's say we want to point at a source 30 degrees away. What we do is we add on a phase delay to each of these antennas so that in this 30-degree angle, the signals constructively interfere. They reinforce each other, and we get a big signal. Now, on the other hand, a signal coming from 0 degrees would have destructive interference, and so we wouldn't see it. So we can point in a particular direction and ignore something from other directions. Now, there's been a big push to do this in a digital way. So what we want to do is we want to put the analog to digital converters as close to the antenna as possible, and then we can capture lots of different signals and point to different directions simultaneously. And here's one we built in the lab. This is from Christine and Rundell. Christine is here today. And you can see the chip over there on the left. We're pointing a source to the chip. We use a lot of Lego in our labs for these things. And if you can see, this is Yoda here. He's our microwave lab god. So another direction we've taken this work is in collaboration with JPL and NASA. And some of you might recognize this picture here. It's the Very Large Array. If you're a science fiction fan, you might have seen the movie Contact with Jodie Foster. It's a Y-shaped array. And JPL came to us and they said, hey, Mike, could you build a system for us to power a weather satellite with a Y array? And this is one of these hard projects that I got Zynga involved in. So they wanted a satellite like this that would point down, and it's a radiometer. It picks out infrared emissions from clouds. So we built this chip here. I did the mixed signal part with my students, and Zynga did the part in the middle. And we built this chip, and it worked first time. And JPL brought it up in the lab. And this is the satellite system on the ground. And what they're doing here is they're imaging a building. And the building, they're picking up the infrared emissions. And you can see there's somebody waving there that's being picked up by the system. Right? So another direction that we've been taking this kind of research more lately is in speech recognition. And this is a really interesting problem. There's a lot of privacy concerns about this. You have a device that could be listening all the time. You'd like to have the processing local, and you're very concerned about the efficiency of this and the power consumption. And speech recognition is actually a very tough problem. It's easy in a quiet place like the Michigan Library, but in a noisy environment, it's really tough. And that's called the cocktail party problem, right? You know, humans are actually very good in that situation, but machines are really bad. So let's see what humans do. Well, the human ear, it's got this amazing device called the cochlea. And what the cochlea does is it breaks the speech into different frequencies. So you can see there's kind of different colors being shown here. And so what you get is something called a spectrogram. The horizontal axis here is time, and the vertical axis is the frequency, and the different colors are the different strengths of different frequencies. So there's some word being spoken there, and I'm not sure what word it is, but if you looked at the spectrogram, you could actually tell what the word is. And that's what the neural network in the brain does. So we've been trying to do this with our designs. So we kind of mimic what's being done in the human hearing. So we have, you know, some sort of analog digital conversion, we produce a spectrogram, and then we have some sort of machine learning where we classify the signal. Of course, we've got ADCs in there. But the problem is when you bring noise in there, the efficacy of the system really degrades very quickly. So if you take a kind of a hint from what humans do, humans have 2 ears, and with those 2 ears, you're doing beamforming. So it's just like the wireless system. So we add on multiple microphones, and using the multiple microphones, then we're able to dramatically increase the efficiency of the speech recognition. So those are some interesting applications that we've been working on. And those have been really hard, but they've been a lot of fun for me and my students to work at. But now there's a new direction that we're starting to look at, and this is where the back again comes in. And, you know, we're very familiar with digital computing, but before digital computing, there was analog computing. And there's some amazing analog computers out there. This one is called the Old Brass Brains, or the official name is Tide Predicting Machine number 2. And this was used by the US government from 1912 to 1956 for predicting tides. It's a completely mechanical computer. And apparently it worked really well. And then along came World War II, and there was a real explosion in analog computing. And one of the more famous ones, or infamous ones, is the Northern bomb sight, right? So the Allies, especially Americans, used these bomb sites when they were, you know, carpet bombing Germany during World War II. Now, the idea behind these bomb sites is that they would make bombing, you know, very, very accurate because they would model things like the speed of the plane, the wind speed, and so on. In practice, it didn't help at all. The bombing was, because the information was just so bad being fed into it, that they ended up, you know, it was almost as good just to look out the window of the plane and just drop the bomb, right? But these were very, very sophisticated analog computers. Now, nowadays, we have this huge explosion in computing due to AI and machine learning. So let's talk about that for a minute, and let's see where that's going. And in machine learning, often we're trying to classify something. So maybe there's pictures of dogs and cats, and we'd like to figure out, well, which one is which. And, you know, things like Google are fantastic for that. Now, the problem with this is this has been so successful that the energy consumption required for this is just humongous. So right now, AI and machine learning are taking about 10% of the US's electricity production. It's absolutely staggering. And the future looks pretty bleak. Well, if you see the growth in computing, currently we are at 1 Zappa instructions per second, which is 10 to the power of 21 instructions per second, right? And this is going to increase with the, along that line here, but the line is really showing the energy consumption for this computing. So on the top here is the world's energy production, and what we're going to see is with the current progression in computing power consumption, it's going to exceed the world's energy production in about 20 years. Obviously, this can't happen. So the only way for continuing increasing computing is to make computing more efficient. Now let's look at what the state of the art is. The state of the art is something like a GPU, which people use for like Bitcoin mining and so on, but also for AI. Or you could use a programmable logic thing like an FPGA. Now those give you about maybe 1 to 10 tops per watt. We need to get several orders of magnitude improvement to meet the requirements for computing. Now, another option is maybe a digital ASIC. So this is one from Google. It's a tensor processing unit, what they call it. Now, that gives us about an order of magnitude improvement, but it's not getting us there. Now, let's look at the operations that we need to do in some sort of machine learning system. Well, this is a simple machine learning stack. And you have an input coming in, and on the right then is the output, the decision, right? And what these stacks do is mostly they're convolutional layers. So all that means is they do a lot of vector matrix multiplication. So the thing is, analog can be really good for vector matrix multiplication. So I want to show the first schematic with devices today. This is the only one. This is about as complicated as it gets. So if we have a matrix of resistors like this, and we connect them in a crossbar, and on the left we put in voltages, and on the bottom then we're going to look at the currents coming out. Well, the currents coming out are going to be the vector matrix multiplication of the resistor values times the input. So we get this analog multiplication, and it's going to be super efficient. Now, to use this, we're going to come back and have to put on analog to digital converters and digital to analog converters. And this is one of those hard projects that I worked with Xing and Zhang. And we also had Wei Lu involved, but we got some recognition for this. This was a Nature cover a few years back. It was the first single-chip analog memristor compute engine. And over the last few years, we've followed up in a collaboration with Applied Materials. And this was the closest thing I've had. I worked in a startup before coming to Michigan. And this project was really hard. It was like running a startup. There was 10 or 12 PhD students involved. And we built this chip, and it worked first time. And we got 600 tops per watt. So that's almost 2 orders of magnitude better than the Google system. So that's kind of where things are going. And I just want to give you a peek at some of the future projects that I'm starting to work on. So, analog to digital conversion and that interface will always be the key thing, but we're getting kind of really interested in the applications and doing some really wacky and wild things. So one of the areas we've been working on, and this is being funded by a new project from the National Science Foundation, this is active acoustic metamaterials. So if you ever saw Get Smart from way, way back, there was the cone of silence. So we're going to try and build a cone of silence. We're going to try and make acoustic holograms as well. It's going to be interesting. So I don't know. John is there. He's going to work on it and figure it out. New students, you can ask them to do anything. Maybe warp drive next. We've got a new project with DARPA. This is also with Xing, and this is quantum-inspired computing. So quantum computing is wonderful, but it's super expensive. It turns out that you can kind of do a poor person's quantum computing with analog circuits, with things like oscillators. So we're going to try to do that. And another new project is an SRC project. This is with a group of people from Michigan. It's called Sensing to Information. It's new ways of converting between analog and digital and making sense of things. So the very last slide, it's a little bit provocative. This is from a recent book from David Sachs. And it says the future is analog. And he's not an analog designer, but the kind of premise here is kind of interesting. So basically, he views the last few years, especially with COVID, where everything went digital, as being something where we all lost a lot because we didn't have, face-to-face interactions. We had these digital interactions. And when we were experiencing things, we weren't experiencing the real analog things. We were experiencing some sort of digital version of those. So it's an interesting book, and that's it, and I'd love to take your questions.
So I have a question, and I'm going to apologize if it doesn't make any sense.
Oh, sure. Go, sir. Yeah. Right.
Depending on where you are and the technology, you attribute, and I'm curious your answer to this, you attribute this to huge advances in machine learning and just faster CPUs, do I assume you...
Yeah. Right. Yeah. Right. I mean, there's a lot of things that 20 years ago were considered science fiction, like speech recognition was something that nobody ever thought that would get working well. And now it works pretty well, except for noisy environments, right? A lot of the contributions there have been on the machine learning side. Machine learning is just so good. But also to make the machine learning work well, you need to get the high fidelity digital representation coming in. Like something like the Amazon Echo is kind of interesting because you can talk to the Echo while it's playing music. So for that to happen, the Echo has to digitize not only what it's producing, but also the signal that you're giving. And there's a huge dynamic range there. So the AI has gotten much better, but the analog to digital interface has also gotten so much better in dynamic range. I don't know. I think a lot of it is just the machine learning is just made so much. Like the thing about machine learning is machine learning was only kind of a curiosity until about 15 years ago. And what happened is when the networks get to a certain size, they start to work well. That's what happened. And then they could just make big enough. And Jan can answer better than me, but yeah.
No, we got to ask Mike more.
Yeah.
How fast you could do, what frequency?
Oh, I see. Yeah. I know.
Where can we go with that?
Oh, okay. Yeah. That's kind of it. That's a really tough problem as well. In my group, we max out at about sampling at about 6 to 10 gigahertz, right, which is pretty fast. There are people out there who build these converters that run up to over 100 gigahertz, which is incredible. I mean, you're 0.1 of a terahertz, right? And it turns out the application for those is for data links. So, you have these compute centers and there are these huge switches that get all the data flowing in the right place. I think Boston is here, Boston works on that. And they have these very, very high bandwidth data links. And to make those data links work well, they need these analog digital converters to work at these sub-terahertz rates. So those are possible, they're very hard to design.
It's causing the feedback.
Okay, we turn it off.
Yeah. So it used to be that memristors were a bit of a controversial topic. I don't know if that's still true, but there's an alternative approach out there called computing in memory.
Oh, I see. Right.
Which you're probably familiar with from Purdue, I think it is.
Yes.
They're a little bit disingenuous because they take memory cells and then add a couple of transistors to get analog functions.
Right.
To create a current that they sum up just like you did in the memristor case. So
yeah.
If you're familiar with that, how would you compare those two approaches?
Okay. So I showed there the crossbar with the resistors, and to make that work, you need to be able to program the weights. So that means you need a programmable resistor, and the programmable resistor is something called a memristor. And my colleague Wei Liu is kind of a pioneer in that. He's got a company, and he's done so much, made so much progress there. So we were going the truly analog approach, so we needed those programmable resistors. So a completely analog approach needs those programmable resistors. Now Dave is talking about an approach which takes a conventional digital memory cell, and you can sort of get part of the effect with a digital memory cell. Now, in some sense, that's easier to do because you don't have to work with this messy device. And those work quite well. The memristor devices, if we can get them to work sufficiently well, there's more potential there. Now, it's not clear yet whether the memristors will be good enough. There's a lot of money going into this, but I don't know if it's going to work. Yes. Yeah.
You look up how analog to digital converter works in
Right.
Google or Wikipedia, you always see a voltage in and bits out. But
Right.
in the real world, things aren't always voltages. Is there much work or much opportunity on, say, capacitance to bits or inductance?
Yes. Yeah, people do that as well. Like for fingerprint sensors, those are capacitive to digital sensors. There's current to digital sensors. Very often people take a sensor output and convert it to voltage, maybe because it's a bit more convenient and because you need gain. But you can have it where you have something that's closer to the sensor signal, like you're saying. Absolutely.
Could you elaborate just a little bit on you mentioned future efforts in the quantum computing area?
Oh, I see. Yeah, the quantum computing stuff. Yeah, so the background for this, about a year and a half ago, I was running out of money, so I was looking for interesting things to write proposals in. This is what happens, it's a feast of famine. And I saw this call from DARPA. It said quantum-inspired computing. And it was in the middle of COVID. I was home, so I had plenty of time to work on stuff. So I read up about this stuff, and it sort of makes a little bit of sense, right? Now, the idea of it is that, qubits have multiple states, right? Usually 1 and 0, but the beauty of quantum computing is those states exist at the same time, right? Now, what DARPA wanted to look at was something that could give you the advantage of quantum computing, but on a much cheaper scale. And one method of doing that possibly would be oscillators. There are different kind of analogies you could have, but oscillators are one. And if you have a network of oscillators, you can have those oscillators coupled to each other, just like qubits would be in a quantum computer. And you can represent the state as being phased. So you could have 0 degrees and 180 degrees. So you could have, depending on the network conditions, the oscillator phases would resolve to satisfy the network requirements. So they would solve a problem. They don't have the superposition ability, but they can evolve to solve a problem in a way that's kind of like, maybe more like simulated annealing than quantum computing. But it's a sort of an interesting approach to apply analog to solve these very hard, NP hard problems, right? So it's kind of exciting. I'm not sure if we can make it work, but we'll take DARPA's money for a while. Yeah.
How to write a successful research proposal.
Desperation is what. Yeah.
Yeah, so we talked about vector matrix multiplication. Now, in optics, you can do that like very rapidly.
Yes. And
Because
people do try to do vector matrix multiplication with optics. That's kind of a strand as well for research, right? Now, with that, you need to be able to, the challenges then are getting in and out the information, right? So that causes power. And then having programmability as well, but it's definitely a way to go, right? And there are some one of my former students works for a startup company doing that, right? So it's definitely a way to go. I don't know enough about optics to try that, so maybe we should talk. Yeah, John?
Yeah, hi, Mike. Really enjoyed your talk. Since you are specialized in ADC, I have to ask a question about ADC.
Yeah.
So the ADC is always, for example, is always like in your example, scale half.
Yeah.
Are there some more intelligent ADC that if they know the problem way?
Right. Yeah. I should say that John and I collaborate on systems for nuclear detection, right? So this has been another hard collaboration that we have. But so conventionally ADCs are binary, right? But there are other depictions. In the past, we've worked on converters that work in the log domain, right? So, and that's a kind of an area that's kind of interesting. But generally, we need to use digital processing, and that's probably in the binary domain. So those are kind of boutique kind of converters. Yeah. So they're interesting, maybe helpful in some cases. Yeah.
Last question, good.
Hey, Mike, so you showed these resistive networks, right? Where you did this vector matrix multiplication. But can't you do it using reactive networks?
You could, yeah. I mean, the resistive ones are, you mean like capacitors and stuff?
Yeah.
Yeah. You could, yeah, and some people use capacitors. The thing is, the resistors are nice because you can program them, and they're non-volatile weights, right? So, but totally, sometimes people use capacitors.
Capacitors.
Yeah, yeah.
Let's thank Mike.
Congratulations, Mike. I have the pleasure of giving you two mementos. One is your medal.
Oh, wow.
For official events. And Mignon, make sure he wears it for at least a month. Not that he's got it around the office. So there you are. Yep. Chair bears your name and the name of the professor.
It's a cheat.
Try it. See if it fits. Okay, that concludes our program. Please join us on the Masco Lounge for reception.